Have you ever wondered if there's a single theory that can explain everything in the universe? An intriguing question, isn't it? It's the question that has driven some of the greatest minds in history, and it's the question that continues to drive modern physics. What we're talking about here is the quest for a unifying theory of everything, a theory that can explain everything from the smallest particles to the largest galaxies. It's a theory that doesn't just describe the universe as we see it, but one that can predict new phenomena and help us to understand the universe in ways we never have before. At the heart of this quest is the recognition that our current understanding of the universe, the standard model of physics, has limitations. The standard model has been incredibly successful in explaining the world of the very small, the world of particles and forces. It's given us a detailed understanding of three of the four fundamental forces of nature: the strong nuclear force, the weak nuclear force, and electromagnetism. However, the standard model falls short when it comes to explaining gravity, the fourth fundamental force. It also can't explain dark matter and dark energy, mysterious substances that make up about 95% of the universe. And it doesn't explain why the universe is made of matter and not antimatter. In other words, while the standard model has been a remarkable tool, it's not the final answer. It's a piece of the puzzle, but it's not the whole picture. We need something more. We need a theory that can truly unify all the fundamental forces, all the particles, and all the phenomena of the universe into a single, coherent framework. So, if the standard model can't explain everything, is there a theory that can? That's the question we'll be exploring in the following scenes. Stay tuned as we delve deeper into the mysteries of the universe and the quest for a theory beyond the standard model. To understand why scientists are looking beyond it, let's first understand what the standard model is. Picture the universe as a grand cosmic puzzle, with each piece representing a distinct element of matter. The standard model is our current guidebook, helping us understand how these puzzle pieces interact and fit together. At the heart of the standard model lie the four fundamental forces. First, we have gravity, the force that keeps our feet on the ground and the planets in orbit. Then there's electromagnetism, governing light, electricity, and magnetism. The strong nuclear force holds atomic nuclei together, preventing them from tearing apart due to electric repulsion. Lastly, the weak nuclear force, which is responsible for radioactive decay and nuclear fusion in stars. These forces are carried by specific particles known as bosons. For instance, photons carry the electromagnetic force, while gluons carry the strong nuclear force. W and Z bosons are responsible for the weak nuclear force. Then there's the world of matter, made up of fermions. Quarks and leptons are the two main types of fermions. Quarks make up protons and neutrons, and leptons include electrons and neutrinos. And let's not forget the Higgs boson, the particle associated with the Higgs field, which gives other particles their mass. These elements form the basis of the standard model, a remarkably successful theory that has been confirmed by numerous experiments over several decades. It provides a comprehensive picture of the fundamental particles and their interactions, explaining almost everything we observe in the physical world. However, it's not a complete picture. The standard model doesn't include gravity, for instance. It also doesn't account for the mysterious dark matter and dark energy that make up most of the universe. Nor does it explain why matter prevailed over antimatter in the early universe. While the standard model has been incredibly successful in explaining many aspects of our universe, there are still mysteries it cannot solve. Hence, the quest for a theory beyond the standard model continues. So, what are these mysteries that the standard model cannot solve? For starters, let's take a moment to consider dark matter. Now, despite its ominous name, dark matter is simply matter that we can't directly observe. This elusive substance doesn't interact with light or other forms of electromagnetic radiation, making it virtually invisible. Yet it's estimated that dark matter makes up about 85% of the universe's total matter. The standard model, however, doesn't account for it, leaving a substantial gap in our understanding of the cosmos. Next up is dark energy, another elusive character in the cosmic drama. Dark energy is thought to be the driving force behind the accelerating expansion of the universe. It's a sort of anti-gravity, pushing galaxies apart and stretching the fabric of space-time itself. But just like dark matter, dark energy is not explained by the standard model. Its nature and origins remain one of the biggest mysteries in physics. Finally, there's the question of gravity's place in the standard model. The model does a commendable job of explaining three of the four fundamental forces of nature: the strong nuclear force, the weak nuclear force, and electromagnetism. But when it comes to gravity, the standard model falls short. It simply doesn't provide a quantum theory of gravity, creating a significant inconsistency in our understanding of the universe. And there you have it, the invisible dark matter, the enigmatic dark energy, and the puzzle of gravity. These are the compelling mysteries that the standard model cannot solve. They remind us that our current understanding of the universe, while impressive, is far from complete. They challenge us to question, to explore, and to innovate. These are the mysteries that have led scientists to search for a theory beyond the standard model. One of the most promising candidates for a unifying theory is string theory. It's an idea that dares to dream big, aiming to tie together everything we know about the universe into a neat mathematical bow. At its heart, string theory proposes a fascinating concept. What if all the particles we observe are not point-like dots, but tiny vibrating strings of energy? These strings, it suggests, vibrate at different frequencies, and it's these frequencies that give rise to the particles we know and love, electrons, quarks, neutrinos, and so on. But string theory doesn't stop there. It goes a step further, suggesting that there are more dimensions to our universe than the three of space and one of time that we're familiar with. In fact, most versions of string theory propose that there are 10 dimensions, with the extra ones being compacted so small that we can't observe them directly. So how does string theory tie into the quest for a unifying theory? Well, one of the biggest challenges in modern physics is to reconcile the world of the very small, described by quantum mechanics, with the world of the very large, described by general relativity. These two theories work incredibly well in their respective realms, but when you try to combine them, things get messy. This is where the concept of quantum gravity comes in. Quantum gravity is the attempt to reconcile these two theories to create a quantum theory of gravity. And string theory might just be the key. It suggests a way in which gravity, along with the other three fundamental forces, could arise from the vibrations of these tiny strings. It's an elegant idea, but it's also a bold one. It requires us to rethink our understanding of the universe, to accept that there might be more dimensions than we can perceive, and to accept that at its most fundamental level, our universe is made up of tiny vibrating strings. Although promising, string theory is not without its challenges. But then again, what worthwhile quest isn't? As we continue to delve deeper into the world of the very small and the very large, who knows what we might discover? So, what are these challenges and what lies ahead in the quest for a unifying theory? Well, as we delve deeper into the realms of the unknown, string theory, a leading contender in the pursuit of a unifying theory, faces a significant hurdle: the lack of experimental evidence. You see, string theory operates on scales so minuscule and energy so immense that we currently lack the technology to directly test it. It's like trying to read a book that's on the moon with just your naked eye. In addition to this, the theory itself is incredibly complex, requiring a whopping 10 dimensions, 6 more than we're used to in our everyday life. It seems our universe is a lot more complicated than we thought. And let's not forget about the landscape problem. String theory allows for a vast number, perhaps even an infinite number of different solutions, each corresponding to a different universe. This makes it challenging to pin down which solution describes our own universe. But let's not lose hope just yet. Challenges are merely stepping stones in the path of progress. Theoretical physicists around the globe are working tirelessly to devise ingenious ways to test string theory and other potential unifying theories. They're exploring novel concepts, from the intriguing idea of parallel universes to the mysterious nature of dark matter and dark energy. In the future, breakthroughs in technology could open doors to new experimental tests. Giant particle accelerators, more powerful than anything we've seen before, could provide the crucial evidence needed to support these theories. And advances in quantum computing could help us decipher the complex mathematics that underpin them. So, as we stand on the precipice of scientific discovery, the future prospects for a unifying theory look promising. Despite the challenges, the quest continues, fueled by our insatiable curiosity and our relentless pursuit of knowledge. While the quest for a unifying theory continues, one thing is certain: the journey of discovery is as exciting as the destination itself.